Let's take a look at the continuity lesson in the limits chapter. And for this particular lesson, we're going to start off with a very basic warm-up where we're given a few graphs below. And there's a general question that we generally start off for this particular lesson, and that is, can you draw these graphs below without lifting your pencil? Okay, well, so for this very first graph, I can definitely draw this graph in green without lifting my pencil. So for sure, this answer is yes. So that kind of looks like a trig graph, or maybe it's a polynomial graph, but I can definitely draw that without lifting my pencil. For the second graph here, I have a linear line here, so I can definitely draw that without lifting my pencil. And for this third graph here, I got this vertical, I have this V shape here, maybe an absolute value function, and I can definitely draw that without lifting my pencil. Okay, so it looks like the first three graphs, they all have one similar pattern here, and that is they're very easy to draw, and we can kind of say that they're continuous, which kind of falls in line with this lesson here, which is called continuity. Now for the next two graphs, I definitely need to lift up my pencil, right, in order to draw these graphs. So if I draw this linear line here, and then there's a hole there, and then I need to continue the graph over here. So a classic piecewise function, and there's a hole right here. And in my next graph, I have a classic rational function where there's a vertical asymptote at x equals to 3. So for these graphs, I definitely need to lift up my pencil in order to draw them. So it seems to be those last two graphs are not continuous. Okay, so let's take a look at some of these notes here now. Some of the graphs cannot be drawn without lifting your pencil, in particular these last two. And what's preventing us from drawing those graphs without lifting your pencil? Well, one of the graphs has a hole because it's a piecewise function, and for a rational function, we have a vertical asymptote. So those kind of features cause these interruptions in the graph where we have to lift up our pencil in order to draw the graph. Okay, so if I had to informally, define the term continuity, for now, I just have, basically graphs that we can draw without lifting our pencil. And some of the graphs that did come up where we could draw them without any problems were these polynomial functions and these absolute value functions. Okay, let's try to now come up with a more of a formal definition of the term continuity. And before we do that, let's take a look at a few more graphs here. So I have this graph of f of x, which is a quadratic below. And the first question I want to ask is, can you draw this quadratic without lifting your pencil? And the answer is yes, because a quadratic function is it's a polynomial function, and as you can see with this green line here, I can definitely create this. I can definitely cover that entire graph without lifting up my pencil, so it looks continuous. Another question I want to ask is f of -2? Does it exist? Okay, so where is the x value of? This means when x is equal to 2, does the function exist? Well, here's -2, and if I go straight up, I definitely have a coordinate there, and that coordinate is -2, 5. So definitely the function does exist when x equals -2, and the value of -2 is 5. Okay, another question I have is, does the limit exist when I approach -2? Okay, so since this is the overall limit, the very first question is, does the left-hand limit exist? And the answer is yes, because on the left-hand side, highlighted in purple, we reach a height of 5 when I approach 2. And then if I approach -2 from the right-hand side, I reach a height of 5. And therefore, I can definitely say here that the left-hand limit equals to the right-hand limit. And therefore, yes, the limit does exist. And the value of the limit is +5. Okay, for part D now, what do you notice about f of -2 and the limit as x approaches -2? Well, they're both equal to 5, right? So let's just say they're both equal to 5. Okay, so now do we think f of x is continuous at x equals -2? I think yes, because I can draw this graph without lifting my pencil. And it turns out that the function and the limits are of equal value when x equals to -2. Okay, let's take a look at another graph here. Now we have a linear line g of x, and first question here is, does g of 3 exist? Okay, when x equals to 3, do we have a y value? And the answer is yes. This is g of 3 right there. So the answer is yes. And g of 3 equals to 0. Now, does the limit exist? Okay, well, the limit definitely exists on the left-hand side, and the limit definitely exists on the right-hand side, so I'm going to say yes. The limit does exist because the left-hand limit equals to the right-hand limit, and the overall limit equals to height of 0. And what do we notice about g of 3 and the limit as x approaches g of 3? Well, they're both equal to 0. Okay, and then finally a follow-up question here is, do you think g of x is continuous at x equals to 3? And I will say yes, because I can draw this graph without lifting my pencil, and it looks like that the limit and g of 3 when x equals to 3, they're both equal because they have a value of 0. Okay, so in calculus, the term continuity has a 3-part definition, and based on our 2 examples that we just finished, what can we put together here to now put together a more of a formal definition of continuity? So we don't want to say lifting up our graphs that we can draw without lifting our pencil all the time. We want to have a more of a formal definition. And our formal definition will start off like this. First of all, the function has to exist at the x value. Okay, so f of a has to exist. Okay, so this a is the x value, so the graph actually has to be defined for the x value that you're looking at. In our previous graphs here, in our previous example, our a value was 3, and so if we're looking at x equals to 3, the graph has to exist when x equals to 3, right? So that's the first part of the definition. The second part of the definition is that the limit, when x approaches that a value of the function, it has to exist as well, right? So if the limit exists, that means the left-hand limit and the right-hand limit have to be the same, and that will mean the overall limit is defined. Okay, and for the third condition, we have to make sure that the function equals to the value of the limit when x approaches a of f of x. Okay, so if these 3 conditions are met, then we can say that the function is continuous, and that will allow us to draw the graph without lifting up the pencil. Okay, let's take a look at a few example questions here. And first of all, let's go over a very classic question here where we're given a piecewise function, and I'm given this quadratic function there and a radical function there. And I guess our a value here is going to be 0. So we want to know, is this graph continuous? All right, so is this continuous when x equals to 0? Okay, so what I'll do first here is I will go ahead and maybe just draw a little sketch of this graph here, and the graph kind of looks like this if you went ahead and graphed this on Desmos, something like that, and then the graph kind of goes off like this. Okay, and we have the x value of 0 there. So this is a piecewise function there, so I have a radical function and I also have a parabola, and can I draw this without lifting up my pencil? And the answer is yes, so it looks continuous at x equals to 0. But now let's go ahead and apply the 3-part definition in order to verify that the function is continuous when x equals to 0. So if the first part of the definition is, does f of a exist? Okay. Well, we know the a value is equal to 0. And if I take a look at my piecewise function, this is super important here. If I look at the piecewise function and the boundaries here, I hope it's clear that in this bottom graph, the function is defined when x equals to 0. So I'm really looking at the radical function in this case. Okay, so if I have f of 0, I'm going to plug the 0 into my radical function because that's where the function is defined when x equals to 0. So I can put my 0 there, plus the 1, plus the 2. And if I evaluate f of 0, I get a nice answer of 3. So does f of a exist? The answer is yes, and that's because the value is 3. Okay, and for part 2 now, does the limit exist? Does the limit exist when x approaches a of f of x? Does this exist? Okay, well in this case, what we need to do is we need to show that the left-hand limit is equal to the right-hand limit. Okay, if I look at my boundaries one more time again, which of these functions, the piecewise functions, which function is on the left-hand side? And clearly that should be the top function here, because if you're less than 0, you are on the left-hand side of 0. So this function right here is the function that represents the left-hand limit. Okay, so if I write my limit statement here, LIM, as x approaches 0 from the left, the function that I'm dealing with is the quadratic function, which is x squared plus 2x plus 3. And then I need to make this equal to my right-hand limit as x approaches 0 from the right. And if I'm approaching 0 from the right, I'm actually dealing with this function at the bottom here, because the radical is defined for when x is greater than 0. So this is 0. If I'm greater than 0, this is the right-hand side, right? So this represents the right-hand side of the function. So this will be the square root of x plus 1 plus 2. Okay, I'm running out a little bit of space here, but if I go ahead and now just kind of do our direct substitution here, it turns out that I get 3 on the left-hand limit, and I also get 3 on the right-hand limit. So since the left-hand limit equals the right-hand limit, the limit does exist. Okay, so it turns out that the function when x equals to 0 and the overall limit, they're both equal to a value of 3. So therefore, the function is continuous. Okay, so the function is continuous at x equals to 3. And clearly from this graph, the function is continuous. The left-hand limit and the right-hand limit are both equal to a value of 3 here, and the function f of 0 equals to 3, so therefore this function is continuous. We can draw it without lifting our pencil there. Okay, so that's it for that question. Another question that we sometimes get is we need to find the values of k so that this piecewise function will be continuous at a certain x value, and this x value is x equals to 4. Okay, before I do a question like this, if you actually went to Desmos here, and you don't need to write this down in your notes here, but basically when you see these kind of problems, and if you try to graph this onto Desmos initially, sometimes the problems may look like this when you're plugging this into Desmos. And what you want to do is you want to try to connect these two graphs together by making sure you can find the value of k that will actually connect these two graphs together here. So right now the graph is broken, and what we want to do is we want to find the value k so that these graphs can be connected, and then you have a continuous function there. Okay. So since you're forcing this function to be continuous, you can pretty much jump to the third part of the definition. And the third part of the definition is that the function when x equals to a has to equal to the limit as x approaches a of f of x. All right, so this is the third part of the definition, and this must be true for the function to be continuous. Okay, so our a value is given to us as always, which is 4. So if I write this in, I get f of 4 equals to the limit as x approaches 4 of f of x. Okay, so let's go ahead and figure this out here. What is f of 4? Okay, so when I look at the function here, this bottom function, if you look at this equal sign right there, the bottom function includes 4, so therefore our function, our f of 4, is going to be replaced with x squared minus x. Okay, and then we're looking at the limit here as x approaches 4. And since we've used the bottom function already, the bottom function is now gone. The only thing that's left over is the top function, which is kx plus 5. Okay, and this will allow us to satisfy the third condition here. Okay, so all we do now is we plug in 4 for the x values here. So this will be 4 squared minus 4. And this will equal to the limit as x approaches 4. Actually, instead of doing that, let's just go ahead and just solve the limit problem here, because if I have a 4 here, all we do is just plug that in there, and we get k times 4 plus 5. Okay, now we have enough information to solve for k here, so this will be 16 minus 4. This will be 4k plus 5. If I subtract 5 from both sides, I guess I have a 12 there minus the 5. So therefore I have a 7 here, and I have a 4k here, and that means k would equal to 7 over 4. Okay, so the value of k is 7 over 4. And if I went back into Desmos or back to my original function here, and if I let k here be 7 over 4, then these two functions would be continuous. Okay, so if you had to like graph this final answer here where you do have your k value here, so basically it would kind of look like this. There's one part of your graph. This is the x value of 4. I guess the y value here would be 12. And the next part of the graph will give you this linear line like that. And that would make the function continuous there when k equals to 7 over 4. Okay, so I would definitely ask students to maybe put this function into Desmos and graph it, and then you'll see that the graphs will be connected, and then you force this problem to be continuous. Okay, so that's good. That's pretty much all I'm going to cover for the continuity chapter. I would say that the homework questions are very similar to this last one here. I would say one more thing I'm going to finish off for this particular lesson is just kind of going over the intermediate value theorem. So if you ever see the intermediate value theorem, you might see me write IVT. And we kind of saw this in one of our questions at the start of the year. And basically what the intermediate value theorem, what this does is that this is like an existence theorem. And basically how it works is that if you have some kind of graph f of x, in this case, here's my f of x graph. It's just some polynomial function, I guess. And we say that this function is continuous on this interval. Now, this interval is really your domain. Sometimes the domain is kind of written as this. So they're your x values that represent your domain. And if we're given that if f of a is less than 0, meaning you're below the x-axis, and if your n value over here is above the x-axis, then you must have at least one x-intercept in that domain. And hopefully that makes sense, because if I take a look at this point right here, the y value here, the y value there, which is f of a, this is definitely below the x-axis, right? And then if I look at b here, I mean, clearly the y value here, which is f of b, the y value here is above the x-axis, right? And if this function is continuous, continuous means you can draw this without lifting your pencil, then if I draw this graph here connecting the endpoints, then we must have at least one x-intercept, right? And that's the intermediate value theorem. Okay, so maybe the graph looks like that, but maybe the graph could also look like this, right? I mean, is this a continuous function? Can I draw this without lifting my pencil? The answer is yes. And notice that we have at least one x-intercept. In this case, we have a few of them. But the intermediate value states that if you have an x value here, that gives you your y value to be less than 0. And if you have your y value at this other endpoint, which is greater than 0, and if you have a continuous function, then you must have at least one x-intercept in that domain, which is from A to B. Okay, so let's go ahead and just do one quick intermediate value theorem, and then we can finish off this homework, this lesson video here. And this is kind of like the conclusion of the intermediate value theorem here, so that this c, this c is kind of like your x value in your domain. And what we're saying is that there's one x value where your y height is 0, and this is really your x-intercept. Okay, so I was a little bit fast there, but basically once again what we're saying is if you have your endpoints, if one's negative and one's positive, and if you have a continuous function, then you should have at least one x-intercept in that domain, right? Okay, let's take a look at one example here, and hopefully we can put all this notation together here. And let's just say we have a polynomial here, and we need to show that this equation has a solution in the interval 0 to 2. Okay, so how do we apply the intermediate value theorem? Well, first of all, this is your domain. And what we need to do with the intermediate value theorem is we need to evaluate the x values at the endpoints there. So we need to figure out what f of 0 is, and we need to figure out what f of 2 is. Okay, so these are your x values, right? They're not coordinates, they're just your endpoints on your domain. Okay, so if I plug in 0 into my original function, I get 0 cubed minus 3 times 0 squared plus 1, which equals to, I guess this equals to 1, and clearly 1 is greater than 0, so that means the function is above the x-axis. If I plug in 2, I get 2 cubed minus 3 times 2 squared plus 1. And I guess that equals to negative 3. And negative 3 is below the x-axis. Okay, so since one of your endpoints is above the x-axis and one endpoint is below the x-axis, we can say by the intermediate value theorem, there is at least one x-intercept. In the domain 0 to 2. Now this domain 0 to 2, that's the same thing as x is between 0 and 2, right? Same notation there. And if you look at a graph here, it's very easy to see this in a graph here. So if I go ahead and graph this polynomial function, I mean, this is what it looks like if you graph it out to a few more, if you graph it out completely there. And what we're saying here is this right here is 0, and this right here is 2. So this right here is that domain, right? That's your domain there. And since your x-intercept here, I believe this was 1, right? And 1 is greater than 0, meaning you're above the x-axis. And here's the other endpoint at 2, which is negative 3. And negative 3 is below the x-axis. Clearly, this graph, since it's continuous, has at least one x-intercept in that domain, right? Which is technically right there. Okay, so since, once again, the intermediate value theorem is saying that if you look at your endpoints there, if one's above the x-axis and one's below the x-axis, then the graph, when you connect the dots from, you know, this point to that point, and since the graph is continuous, you must cross the x-axis at least once, and that's called a solution there. Okay, so when we say it crosses the x-axis at least once, that's what this kind of notation is saying right there. Okay, so we've done a few of these. We'll do a few more of these problems in class, but that concludes this homework or this lesson video guide.